Okay. So first, shut up for a second. So first thing is lab exam 3 is this week in lab. And then quiz, I think it's the fourth one. Lecture quiz 4 is at the end of class on Thursday. And then the final, I'm going to write the final to be about, I'm going to intend it to be about an hour and a half. You'll have 2 hours to do it. So you should have plenty of time. It'll be a little longer than the other exams, but not a ton. And that is Thursday, 12/19 at 2 p.m. You probably could have guessed the PM part. Okay. Any questions about any of those? Yes. Yes. Yep. Okay, and then I'm going to go through numbers 3 and 4 from the assignment just to make sure that everyone's thinking about sort of the steps right and stuff. So, okay. Oh, that went into my... Okay, hold on. There we go. Okay, so for number 3, the hinge is at the point A. And so everything's rotating around that point A. We're told that there's a tangential acceleration vector of -4 and a velocity of, -4 in the y direction, +10 in the y direction is the velocity. Okay, so let's start sketching out what's going on. The hinge is over. So the hinge is where it says axis. And so at this point, the body is kind of like this. Okay. And the point that we're looking at is A. Okay. And we're given the distance, the radius of this circle is 0.3. And we're told that the tangential acceleration vector is 0, -4. So tangential acceleration is this way. And the velocity is 0, +10. So the velocity is this way. Anybody have any questions about that yet? Okay, so based on this, we can already figure out the signs of the angular velocity and angular acceleration. So the angular velocity is going to be this way in order to have a velocity in that direction. Anybody have any questions about why that is? Can you follow that? This is counterclockwise, so that angular velocity is going to be positive. And then the angular acceleration is this way. That's clockwise, so the angular acceleration is going to have to be negative. But we can come up with the magnitudes also. But now we've already figured out the directions. We already know that omega is going to be positive and alpha is going to be negative. Okay, so now let's go to the equations. We know that the speed is equal to the absolute value of the angular velocity times r. The speed is 10. That's just the magnitude of the velocity vector. So 10 is equal to this absolute value of the angular velocity times 0.3. And so capital omega is 10 divided by 0.3, which is 33.3 repeating radians per second. Now to turn that into the angular velocity, we just need to think about the sign of it. So the angular velocity is plus or minus this. We already figured out that it's positive, so this is 33.3 repeating.
This is not a vector?
Right, these are not vectors. They do have directions, but it's just a plus minus direction. And now we'll go to calculating the tangential acceleration, or using that equation. The magnitude of the tangential acceleration is equal to the absolute value of the angular acceleration times r. The magnitude of the tangential acceleration is 4. So 4 is equal to a times 0.3. And so a, the absolute value of the angular acceleration, is 13.3 repeating radians per second squared.
Wasn't it negative 4?
Well, the capital omega and the capital alpha are both absolute values. So you just throw away the sign.
Okay.
And so now we'll calculate the angular acceleration is plus or minus the magnitude of the angular acceleration. We already figured out that it's negative. So this is negative 13.3 repeating. Anybody have any questions about either of those? So let's see if it asks for anything else. Oh, okay. And also, so then it asks, is it speeding up or slowing down? If velocity and tangential acceleration are opposite each other, it's slowing down. If angular velocity and angular acceleration are opposite, it's slowing down. So you can use whichever one of those you want. And then it asks for what's the total acceleration. Well, we need one more thing in order to calculate the total acceleration. We need the centripetal acceleration vector. And that is this direction. The magnitude of the centripetal acceleration is v squared over r. We just figured out that v is, we already knew v. V is 10. So this is 10 squared over 0.3. So 333.3 repeating radians per second squared. We know from thinking about circular motion, it's in the negative x direction. So negative 333.3 repeating, 0 for y. And now the total acceleration is just the sum of the two parts of the acceleration. So the tangential was 0, negative 4. Centripetal is this, so negative 333.3 repeating negative 4. Any questions about that? So that's number 3, and now let's do number 4 too. Okay, so okay, so this is number 4. This time it gives us an angular velocity, and we're assuming that the angular acceleration is 0. And we're doing some calculations based on that. Okay, so we can, so both of these 2 points A and B are in circular motion around the axis. So B is in a circular path like this, and A is in a circular path like this. Okay. It's a constant angular velocity of positive 15 radians per second. So that means that it's going counterclockwise. And so now we can think about the directions of the velocity and stuff like that. There's no angular acceleration, which means there's no tangential acceleration because of the equation we have relating those two things. And so for this point B, the velocity vector is this way. The centripetal acceleration is this way. For the point A, the velocity is this way. The centripetal acceleration is this way. Okay, so we just have to calculate these acceleration vectors. The tangential acceleration for both of them is 0. So the centripetal acceleration at the point A is, so the magnitude is v squared over r. We don't know v yet, but we can calculate that using this equation. V is equal to capital Omega times r. And so V is equal to 15. That's the angular velocity, the absolute value of the angular velocity, times 1.2. 150, 180, 18. So the velocity is 18 meters per second. Is that right? Yes. And so the centripetal acceleration magnitude is 18 squared over 1.2. So 324 divided by 1.2. So this is 270 meters per second squared. We can see the direction is in the positive x. So the centripetal acceleration, which is also equal to the total acceleration because there's no tangential, is 270, 0. Any questions about that? Now we're going to do the same thing for the point B. The centripetal acceleration magnitude is v squared over r. We have to calculate the speed of that point. So v is equal to omega times r. I'm going back and forth between little and big r's, but I mean the same thing for both of them. Omega was 15, r is 0.6, and so the speed is 9 meters per second. So the absolute value, the magnitude of the centripetal acceleration is 9 squared over 0.6. So 135 meters per second squared. And so the centripetal acceleration vector, which is the same as the regular acceleration because there's no tangential, that's in the negative y with this magnitude, so 0, negative 135. Any questions about that? And then the last thing it asks is, okay, what if you have an object at these 2 points, that's like, imagine a bug that's trying to stay on this record player as it moves around. What's the force, the net force required to hold it without moving from that location? Well, we know this is the acceleration. And so F net is equal to the mass times the acceleration. So for the point A, F net is equal to, it says for that question that the mass is 0.5 kilograms. And so this is 0.5 times the vector 270, 0. So that's 135 in the positive x direction, 0. And then for the point B, same thing, F net is equal to, this time the mass is 1.5. The acceleration vector is 0, negative 135. And so you get 0, negative 202.5. These are forces. I don't know why I put meters per second squared up here, but these should both be newtons. Any questions about that? Okay, so there's only, there are really only about 4 equations that you could ever have to use in these kind of problems. It's just a matter of like, which equation are you using? What are you given? You're using this equation to find what, that can change around. But the only equations you really can ever use are this equation for centripetal acceleration, this equation relating the speed to the absolute value of the angular velocity. And, and we don't have it here, but the other one is this equation relating the magnitude of the tangential acceleration to the absolute value of the angular acceleration. There's not much else that I can ask with kinematics. Okay, so now the next and the last topic that we're doing in this class is rotational kinetics. And remember, kinetics are where you combine kinematics with the causes of the motion. So that's what we're talking about here. So we're combining now rotational kinematics with the causes of rotational motion. And the big equation, well, remember with particle kinetics, the big equation was Newton's second law. The big equation for rotational kinetics is what I'm going to call the rotational version of Newton's second law. Rotational version of Newton's second law. I'm going to call it R N2L, rotational Newton's second law. And it says this, add up all the moments, and you can also call moments torques, those are synonyms. So, but add them all up, and that has to be equal to the moment of inertia times the angular acceleration. This moment or torque, remember that that's like a rotational version of force. And this I is a rotational version of mass. Okay, and so if you think of those that way, this is just Newton's second law, just with rotational versions of everything in it. Okay, so it should be easy to remember this. Before we can use this, I have to define these two things that we haven't defined yet. So first I have to define the moment, that's m, and the moment of inertia. That's capital I. Okay, so when we did particle kinetics, which one did I define first, mass or force? It was mass because it's the simpler one, it's not a vector. And the definition I gave you was a body's resistance to acceleration, if you remember. So you can think of this sort of the same way. We're going to define moment of inertia first. And this is always a positive number. And this positive number is large if the object is hard to start rotating and small if the object is easy to start rotating. Okay, now we're not talking about with friction or anything like that. We're always imagining this object in a frictionless environment, but still some objects are easier to start rotating than others. A marble or something, you can take it between your fingers and start it rotating. But even on frictionless ice, like a semi-truck, it would be hard to get it to start rotating. It's not the friction or anything like that. It's just it's the amount of mass and how the mass is distributed, okay? So to get a high value of moment of inertia, the mass has to be distributed far from the hinge. Something where its mass is spread out far from the hinge is something with a high moment of inertia. And a low moment of inertia is something where the mass is distributed close to the hinge. Okay, so let's think of an intuitive example. So think about like watching the Summer Olympics and watching gymnastics or diving, and you'll see people doing flips, and you'll see people's bodies in different positions as they do flips. And two of the ways that you'll see are people do flips in a position like this, like fetal position, flipping around this way. And then you'll also see people doing flips like this. Okay, and you can imagine that this is the same person in both of these two instances, so there's no change in mass. Okay, it's not the mass that's making the change, but here, if you think about the hinge of this person being the center of mass, so like here for this person and about here for this person, in which one of these two is their mass smushed the closest to the center of mass, the hinge? It's this one over here, on the left, has all of the mass as close to the center of mass as the person can get, as close to the hinge as possible. So this is with the mass close to the hinge. And that means that the moment of inertia is small for this. And that means that this is easy to get rotating. Okay. On the other hand, this one, the mass is almost stretched out as far from the hinge as possible, as far from the center of mass as possible. So here the mass is far from the hinge. That means that this has a high moment of inertia, and that means this is hard to rotate. Well, so like in the Olympics, because it's so much easier to get your body rotating in this tucked position on the left, you get less points for the same number of flips like this, because you don't have to get very high or whatever. You can say you're doing a double flip you can go relatively low and still finish 2 flips this way. But if you're going to finish 2 flips laid out like this on the right, stretched out, because it's so much harder to get your body rotating, you have to get a lot higher in the air. And so that's a lot more difficult. Okay? So that's the idea of moment of inertia. The units for moment of inertia are units of mass times units of length squared and the SI units are kilogram meter squared. Okay, just about all of the shapes that we're going to need to calculate this for are rectangles. So I'm going to give you just a set of formulas for, so this is moments of inertia for a rectangle. But where the hinge is on the rectangle affects how hard it is to get this thing rotating. Okay, so I'm going to give you these formulas one by one. The first one is at A, right at the center of this rectangle. That if you have a rectangle and you're trying to spin it around the center, that's the easiest it can be to get this rectangle rotating. And the moment of inertia is 1/12 times the mass times the, I'm going to write it a different way. 1/12 times the mass times the length squared plus 1/12 times the mass times the width squared. And this is what I'm calling L. And this is what I'm calling W. Okay, the next easiest place to get rotating so just moving the hinge around to different locations. These two are equivalent. So I'm going to call both of these B. And if your hinge is at either one of those points B, then the moment of inertia is 1/12 times the mass times the length squared plus 1/3 times the mass times the width squared. And what I want you to notice as I go through these is the coefficient is always going to be 1/12 for the side where you're in the center. So like in this case of B, we're in the center of the long dimension, but we're at the edge of the short dimension. So the 1/12 is for the long dimension, and the 1/3 is for the short dimension. Okay. Next, these two are equivalent, so I'll call these C. So can anyone think of what the formula would be for this?
Would it be 1/3?
Yep, perfect. 1/3 mass times length squared plus 1/12 times mass times width squared. And then the last one is at any of the four corners. I'll call that D. Now in this case, we're at the edge along the short side and we're at the edge along the long side. So this is 1/3 times the mass times length squared plus 1/3 times the mass times width squared. And so notice it's going from, these moments of inertia are getting smaller as you go this way and larger as you go this way. You could see that by just choosing numbers for L and W and plugging them in. Okay, one thing that is good to keep in mind as you do problems is, kind of the shortest way, the easiest, simplest way to think of it is if I ever leave off a dimension, just treat it like 0, okay? Since L and W are squared in the formulas, you can often treat the shorter dimension as 0 and still get pretty accurate answers. Still get pretty good accuracy. So let me show you an example of how that works. So let's say that we have a board, and let's say it has a length this way of 1 meter, and a width this way of 1/10 of a meter. Okay, so those aren't, the width here is 10% of the length. Those don't seem like that drastically different. But let's calculate, and let's say that the mass here is 10 kilograms. And let's put the hinge at the center. You'd get something similar no matter where you put that. And what we're going to do is calculate the moment of inertia and then compare our answer to making the width equal to 0. See how close we would get by making the width equal to 0. Okay? Like you might look at it and think you're going to be 10% off, but we're going to be way closer than that because the length and widths are squared. Okay? Okay, so if we include that width in there, this formula says it's 1/12 times 10 times 1 squared plus 1/12 times 10 times 0.1 squared. And that gives 0.841, and then 6 is repeating. But now what if we treat that width as 0? So then we get 1/12 times 10 times 1 squared plus 1/12 times 10 times 0 squared. So this whole thing goes away. And what we get is 0.83 repeating kilogram meters squared. Okay, so even though the thickness was 10% of the length, our answers are a lot closer than that. And it has to do with the fact that we're squaring both of these. Like if you square, so what we had here is the length and width were 10% apart, But if you square them both, the width squared is only 1% as big as the length squared. Okay.
But it wouldn't be if we make the number is becoming bigger, we need it then.
Yeah, the closer they are to each other, the more important it is to keep them both. But there's just going to be, you're going to see problems where I don't even give you a second dimension. The implication then is that it's thin enough that it's not even worth
Okay,
paying attention to.
gotcha.
But you might think like, wow, that's got to be really thin. It doesn't really have to be that thin. Being less than about 10% is plenty. Any other questions? Yep. Yeah. Down, did you say?
That's calculating the what?
That's calculating the moment of inertia of this board with the hinge at A.
Like beginning to spin?
Yeah, well, it's kind of, think of it as the same as mass. Like, it doesn't matter what the object's doing, but it's telling you how easy or hard it would be to get this thing to start spinning.
As in like how much force it would take to get it to spin?
Yeah, we're not going to be using force anymore. We're going to be using moment or torque. But yeah, like just like mass tells you how much force you would have to apply to something to make it accelerate a certain amount. Moment of inertia tells you how much of a moment or a torque you would have to apply to something to give it a certain angular acceleration. Okay, so the next thing we have to talk about is what moment or torque is. You can use either of these words. And so let's say you have just some arbitrary object, and let's say your hinge is here. And then let's say somewhere else, there's a force applied. So I'm going to draw it this way. And I'm going to say the place where the force is applied is P. Okay. And I'm going to draw a line here that goes from A to P. And notice that the way I have these drawn, these two things are perpendicular. There's no reason those two have to be perpendicular, but this is an important idea for our calculation, okay? I mean, like, if I applied that same force somewhere else, that red line and F would not be perpendicular, right? There's no reason that they would be all the time. But to define the moment, if the force and the line from A to P are perpendicular, then the moment that that force produces is equal to plus or minus the magnitude of the force times the length of that red line. So this is the distance d. Okay, so you can increase this moment by making this d bigger, by making the distance bigger between these two things, or you can make that moment bigger by increasing the force. Okay, and what about the plus or minus? Well, it's positive if that force would make this rotate counterclockwise around the hinge. And it's negative if that force would make it rotate clockwise around the hinge. Any questions about that?
You said if you make the E bigger, displacement?
Yeah, let me, actually, that's just what I'm about to talk about. So let's say, again, just to understand intuitively what's going on. Imagine trying to turn a bolt that isn't turning very easily with a wrench. And say that you're capable of applying 100 newtons of force to this wrench. Would you have more luck unsticking this bolt by applying 100 newtons of force here? Or 100 newtons of force here?
At the end.
Yeah, and you've seen the big, wrenches that they use for really stuck things or really, and it's just so that you can apply your force as far as possible away from the bolt. Here would be the hinge, okay? The D that I drew up in red above would be from the center of the bolt to where either one of these forces is applied. So if it isn't very stuck, you could turn it by applying 100 newtons of force here. But the more stuck it is, the more you'd want to move that force out. And you'd want as big a wrench as possible. And you probably also can kind of visualize, well, what happened if you just applied a force straight down above this bolt, what would happen? It would never turn. I mean, you could apply 1 billion newtons. It would rip the bolt apart, and it would just be sticking out of the wall, but you still would have never turned it, because you don't have any of that distance perpendicular to the force. So to get this thing unstuck, you can either increase the force or increase that perpendicular distance, or both. And those things have the same effect. Okay, so let me do a quick example. So let's say we have this rectangle. And let's say the hinge is here. And let's say a force is applied here of 30 newtons. And I'll give some dimensions. Let's say the width is 0.25 and the length is 1 meter. And we want to know what's the moment of this force. Well, this is our P, where that force is applied. I'm going to draw that red line that goes from A to P. In this case, those are perpendicular, which is good. We don't know how to deal with anything besides that yet. And so the length of that red line is D, and the moment is plus or minus 30 times D. What's the length of that red line? Yeah, 1 meter. And then if you just think about this one force, would this make the rectangle rotate clockwise or counterclockwise around the hinge at A? Clockwise, and so we want negative. Any questions about that? Okay, I haven't given the units yet. So units for a moment. are units of force times units of length. And so the SI units are newtons times meter. Yes?
Are we gonna need to know the equation for each point of?
They'll be given on tests. Is that, you don't have to memorize it.
At point A, two B's, two C's?
Right, I'll give you that, that picture and all those formulas. You just have to sort of know how to use which one and how to interpret which one to use in a given problem. Okay, so now the next question that comes up pretty naturally is, okay, well, we got super lucky on that example. What happens if that force isn't perpendicular to the line between A and P, right? So what if the force isn't perpendicular to the line from A to P? And the answer is, without changing the problem at all, without changing the behavior, you can always move a force anywhere along its line of action. Line of action. Computer. Okay, the line of action is just, think of that as the line that the force lives in. Okay, so I'll give you an example here. So like if this is the body, and let's say the hinge is here, and there's a force F applied here, okay? Well, to start with, that red line is not perpendicular to the force, right? So I'm going to draw the line of action of this force. That's the line that this force lives in. So it goes on forever. And it's this line. Anyone have any questions about that line of action? And I'm going to just imagine this force being moved to a place where F is perpendicular to that line. So I'm going to take this force and move it to here, okay? It's not even on the body. It doesn't make much physical sense, but that's where I'm going to move it to. And now this is our new point P. And if you draw a line from A to P, now these are perpendicular. And now the length of this red line is the D that you use in the calculations. So let me show you an example. So let's say that here's the rectangle. and it has a height of 3 meters. And a width of 1 meter. And the hinge is right in the middle. And let's say that there's a 20 Newton force here. And a 10 Newton force here. And we want to calculate the net moment. So that's just the sum of the moments from the 20 and from the 10. Okay, well, let's start with the 10. Right now, if you draw the line from A to where that's applied, those aren't perpendicular. That's not perpendicular to the force. So we're going to have to move this 10 Newton force along its line of action. And its line of action looks like this. Okay. So I'm going to move it to right here. And then if you draw the line from A to P, they are perpendicular. Okay. And so the moment produced by that 10 Newton force is plus or minus, the force is 10. What's the length of that red line? 0.5, yep. And if you applied that 10 Newton force, would it make this body rotate clockwise or counterclockwise around A? Clockwise, yep, so negative. So this is negative 5 Newton meters. And now we'll go to the 20 Newton force. And at first, that red line isn't perpendicular to the force, so again, we have to move the 20 Newton force along its line of action. Its line of action is like this, horizontal. So I'm going to move that over to here. Nope, not that far. I'm going to move that over to here. And now the line from A to P is this red line. So the moment from that 20 Newton force is plus or minus the force of 20 times the distance. What's the length of that red line?
0.5?
1.5, because this height is 3.
Oh, shoot.
Do you see that?
Yeah.
So 1.5. And then think again, now this 20 Newton force, would this make the body rotate clockwise or counterclockwise around that hinge?
Clockwise, right?
Clockwise again, yep. And so you get negative 30 Newton meters. And so all together, add these up, and you get that the net moment is equal to negative 35 Newton meters. Okay, so now let's do one where we put all this stuff together and use rotational Newton's second law. So let's say that there's a board attached to the wall by a hinge. And gravity is acting toward the bottom of the page. And let's say that this board has a mass of 10 kilograms and a length of 2 meters. And we want to know what's the angular acceleration of this board. Okay, so for rotational Newton's second law problems, just like with Newton's second law problems, you have to start with a free body diagram. And one thing that you're always going to see in these is the hinge itself applies an unknown horizontal and vertical force. We're going to put those in the free body diagram, but they never come into the calculations, and I'll show you why when we get there. Okay, here's a free body diagram of the board. At the hinge is applying some unknown horizontal and some unknown vertical force. I'll call that Rx and Ry. And then the only other force here is the weight force, and that always acts at the center of the object. Okay, so it's always exactly in the middle of the rectangle is where the weight force needs to be applied. And this is equal to 98.1. And so now we have to go through and calculate the moments produced by all these forces. Well, since those two R forces are at the hinge, the distance from those forces to the hinge is always 0. Okay, so this is what you'll always get. The moment produced by the forces of the hinge is equal to 0. But they should still go in that free body diagram. Then the moment produced by the weight. This is plus or minus the force, 98.1, times the distance from the force to the hinge. So what's that red length?
1 meter.
1, yep. And now would this weight force, this downward force at the middle, make it rotate clockwise or counterclockwise around the hinge? Clockwise, yep, so negative. So we have negative 98.1 Newton meters.
How would you know that? Is it just because the force is down that you just execute?
Well, you just have to, I mean, you could actually do it with like, put a paper on the table and put your finger where the hinge would be, and then apply a force, like in this case it's down. It would make it rotate clockwise around your finger.
Oh, okay, I got it. I understand.
Yep.
How do we know the distance is 1 meter?
Because the length is 2 meters and this is at the middle.
Is that always going to be in the middle?
The weight force always needs to be applied at the middle, yeah. Everything else will be wherever it's drawn in the picture, but the weight force always goes right at the middle.
For a situation like this or every situation?
Every situation, yeah. So we haven't had to think about that before because with particles, everything happens at the same spot. But once we go to rigid bodies, the weight force always has to act at the middle. Okay, so we know that the net moment is the sum of these, so negative 98.1. And now we have to calculate the moment of inertia. Notice that this hinge is in the middle, in the up-down dimension. And at the edge and the long dimension. Okay, so the moment of inertia is going to be 1/3 times the mass times the length squared plus 1/12 times the mass times the width squared, and I didn't even give a dimension. This is one of those cases where we're going to assume the width is 0, and so this whole second part goes away. And so we get 13.3 repeating kilogram meters squared. And now put it all into rotational Newton's second law, and you get negative 98.1 is equal to 13.3 repeating times alpha. And so alpha is equal to negative 7.36 radians per second squared. And then if the problem asks you to calculate the tangential acceleration of some point, you could do that the way we were doing with kinematics before. Or if I had told you that at this instant, this has a certain angular velocity, we could calculate this angular acceleration and then figure out velocity vectors, acceleration vectors of all the different points. That would just be combining what we did today with the rotational kinematic stuff we did last time. Anybody have any questions about that? Okay, so I'll give you a few problems like this to work on, and if you're confused about any of them, I'd be happy to talk about them on Wednesday. We've really covered all the material now. It's just a matter of doing a bunch of examples and things.
Thursday, right?
Thursday, yes. And I will tell my other class on Wednesday the same thing. I don't tell them any secrets. I don't tell you.
But this